Hi there, my name is Alex Fessler, and this is my honors thesis. This was my senior design project called the Coconut Oil Space Cooler for my mechanical engineering major. I worked on this with my teammates Hannah Covington and Largim Zhuta and my advisor, Dr. Lee. So the motivation for this project came from the issue of climate change. As humanity emits more and more greenhouse gases into the atmosphere, our planet will get warmer and warmer, leading to extreme weather events that will affect my generation significantly. This is why my group targeted this issue. We identified that a good way to reduce emissions is to reduce energy consumption. Now, almost a quarter of US consumer electricity use is for cooling your home. So we made that our target area. Our goal was to create a device that can not only cool your room at low power, but also reduce your electricity bill in doing so. To cool the room, we wanted to use phase change materials, or PCMs. So when something melts like ice, it stays at the same temperature, but increases how much heat energy it stores. This is intuitive to us because when we want to cool a glass of water, we put ice cubes in it instead of pouring just really cooled water into it. So this phenomenon of phase change has lots of heat storage potential, which is why we wanted to utilize it. So here's a block diagram that details how the system works. First, warm air is blown across a finned heat exchanger, which is kind of like your car's radiator. The air warms up the water that flows through this finned tube heat exchanger. This warm water is pumped into our PCM heat exchanger, which is a tube-in-tube design. This delivers heat to the PCM, absorbing it, melting, and storing that heat for later. In this process, the water gets cooled down because it delivers its heat to the PCM, which then returns to the finned heat exchanger, completing the cycle and cooling the air in the process. So this project had a few design challenges. First, we needed a PCM that had a melting temperature at a comfortable room temp, because that's theoretically how cold it can get the room. We also needed it to have high heat storage potential. We also needed to have a resolidification process be quick and low energy so that our device is capable for daily use. And finally, we wanted it to be compact and mobile so that it could be wheeled around your house and used in any room. So you may be asking, why coconut oil? Well, coconut oil has a melting temperature of 23.8 Celsius, or about 75 degrees Fahrenheit. This is on the upper end of a comfortable temperature, but it works. It also has a relatively high heat of fusion, which means it can store a good amount of heat while melting. The main reasons we selected it, however, is that it's safe, cheap, and easy to buy in bulk, which is great for the scope of a senior design project. So here's our experiments and results. We put our device in SCU's solar house to see how much cooling it can provide. And we automated this test by measuring air inlet and outlet temperatures with thermocouples, some National Instruments devices, and LabVIEW. This basically just records the temperatures and we were able to plot them. And here are those results. Now, for analyzing heat transfer, it's important to look at the temperature difference between the air inlet and outlet, which is what we've plotted here. As this table shows, we were able to keep an average temperature difference of about 1 degree for 40 to 60 minutes of operation, which is pretty good. Notice though how the temperature difference decreases as time goes on. Well, as the oil around the copper pipe melts, it starts solid, but as it melts, a liquid layer forms that insulates the heat from the remaining solid oil at the outer ring. So the water flowing through the middle has to conduct its heat further to the solid oil. This is what causes that temperature difference to decrease and slows down heat transfer. And soon I'll describe some ideas on how to counter this. So understanding that performance of our device, we wanted to see how well it saves money and power. So looking at this table, you can see that by running our device for an hour during peak times compared to running your AC for an hour during peak times saves literally cents to dollars is the difference. It saves about $1.50 per day. And so if you add these savings up over the course of a month, you'd cut almost $50 off your electricity bill, which is great. Looking longer term, these savings would make your money back in just 5 summers. Looking on the power side, ours uses drastically less power too, which accomplishes our goal of being more sustainable. So in summary, our device has a very cheap cooling option where you can still enjoy cold air while also cutting your bill significantly. So obviously that low power is great, but we want to optimize how much cooling our device can do. So the fastest way to do that is just to choose a different PCM. Either a lower melting temperature or higher heat storage would require no other design changes, but improve our performance a lot. Another way would be to add fins to the copper pipe in our tube-in-tube heat exchanger. This would help conduct heat to those outer layers of coconut oil, as I showed earlier. So in conclusion, our device can cool air by about 1 degree for 40 minutes, runs on really low power, and it pays for itself in just 5 summers. Thanks for watching my presentation, and I hope you enjoyed it. Thanks.